Hi everyone, welcome to this new seminar. And today we'll hear from Gabriele Palloni from the University of Valencia. And so Gabriele is also visiting us for some time. We'll have more opportunities to talk with him next week if you want. But today the topic is about binary boson stars from initial data to gravitational wave signatures. So feel free to ask questions during the talk or at the end. Gabriele, thanks a lot for giving the seminar, and you have the floor.
Thank you. Actually, thank you for giving me the opportunity to talk about my work. I have to say probably the title is quite general, but because this seminar is going to be focused on what I've been doing in my PhD, working with binary hydraulic compact object, and well, I say from initial data to gravitational wave, but actually this seminar is divided in the other way around. So we start from gravitational wave, and then we see how to build initial data. Well, here you see this list of names, a really long list of names, but they're all my collaborators. Well, so let's start. And okay, I would like to do this small introduction in what we are doing. So we know that gravitational wave observation could be quite important, a really strong tool in order to have big knowledge on stellar origin compact objects in principle. Because right now the detectors, in particular the LPK collaboration, is mainly focused on stellar origin compact objects, but in principle they could be able to detect something different, some other kind of compact objects, also known as echoes. And they, in principle, are objects that do not interact electromagnetically with visible matter, but just with gravitational. So they could be a candidate of dark matter for sure. Great attention has been focused mainly recently on ultralight bosonic fields, and this particle can eventually just clump together, forming these, self-gravitating or isoless localized solidons that are a solution of the Einstein-Gregor equation in case of scalar fields, and in case of vector fields, solution of the Einstein-Gregor equation. Now, no proof of the existence has been detected so far, but in principle, if this object exists, they could be found in binaries, and so they can eventually emerge emitting gravitational waves. This is more or less the idea of our work, because if we one day can detect these gravitational waves, we can lead to their discovery, for sure. In order to detect these gravitational waves, we need models, and such that we can build a catalog and then eventually single out the specific signals that we can detect. So this is the goal of my work, and we start with the first of the two work I would like to discuss today. The first part is building this catalog. So we wanted to extend actually an already existing catalog, the one performed by in 2022. In that case, it was considering just a Dol collision of rocket stars. So this is an high degree of symmetry. We want to relax this assumption, assuming orbital angular momentum. So considering now that this system can merge on the equatorial plane. We performed several simulations, and we just consider this spinning M=1 rocket star. Well, here you see the answers, but I think you already know that. And our goal is to observe how the dynamics of the merger and the emission is affected by several parameters, starting from the orbital momentum for sure, the compactness of the equal mass binaries, and for sure the relative phase. I'm going to talk in this talk about in-phase and anti-phase configuration. Just want to tell this now. I refer to in-phase configuration, the one with zero phase difference, so zero phase, sorry, and anti-phase when the phase difference is equal to pi. However, all the results that I'm going to show in this part, at least in this first part of this talk, at least, has been obtained using constraint migrating initial data, unfortunately. But I would like to say just to wait a bit to see how we can try to solve this long living problem, let's say. Okay, let's start with the first parameter, the orbital angular momentum. As I said, we are considering a merger on the equatorial plane. So the boost is along the y direction. And what we can observe directly is that the boost affects for sure the morphology of the gravitational wave emissions, but also the post-merger phase. Let's focus on this plot on the bottom right of the slide. This is one of the less compact configuration. At least so far we consider just in phase binaries because we don't want to spoil eventually other effects. This is the integrated mass in all the numerical grid. So we have the merger, which is represented by this dash black vertical line. And after the merger, the integrated mass drops for sure. So this means that the program cloud just fell in the black hole. However, this drop is not. I mean, the mass does not drop to zero. This means that the curved black hole is surrounded by a short-living program remnant, which gradually is absorbed by the black hole and leaving an important imprint on the gravitational wave emission. Finally, eventually, then going to the funneling down, for sure. Let's move to the second parameter we consider, which is the compactness. Okay, so again, since we are considering just equal mass binaries, we are considering also in-phase configurations. That's an high degree of symmetry. So this means that the dominant mode emission is the quadrupolar mode's emission. Other modes are completely suppressed, at least in this first consideration, and the compactness can also delay the merger time. So for less compact binaries, the pre-collapse and the post-merger phase are longer, as well as the amplitude of the gravitational wave emission. I would like now to move to probably the main parameter that characterize this object. We talk about the relative phase. So the stars are characterized by specific fields, and phase for each field can result to a different orientation of these stars on the equatorial plane. Now, what we want to understand is the relative phase that plays a role rather than the single phase of each star. To do so, we consider these three binaries with the same, for sure, compactness, same orbital angular momentum, keeping the same relative phase. We are considering in-phase stars, but changing the phase of each of the stars. So from left to right, we have 0, pi/4, pi/2. These are three videos of the real part of the scalar potential. Before starting, I want to say several people that saw these videos told me, look, they are like really bright colors. The colors change a lot, really fast. So please try to warn your audience because it's better. So now you know, not my fault. It's something happened. Okay. Let's start with the video. So it's just the dynamics. We see that in general, the merger happens at the same time with the same characteristic. And so the dynamics does not change at all. It's not depending on the single phase of the stars, but on the relative phase. If we focus as well also on the gravitational wave, we can see that it's actually the same waveform for all these three configurations. The relative phase that also a role on the amplitude of the gravitational wave emission. That's a monotonic behavior, meaning that for less compact stars, we can have longer even post-merger phases, but in particular greater amplitude on the emission. While the other way around, we can observe for more compact configuration, more compact stars. So the minimum of the amplitude of the gravitational wave emission is reached in the antiphase configuration. However, this is not probably the most interesting result because what we can observe is the triggering of some odd modes. So if we assume configuration in which the relative phase is neither the in-phase nor the antiphase value, we can end up to some kind of certain kind of asymmetries. This means that due to the interference pattern of the two fields, this implies that odd modes could be triggered, and their contribution is no more like negligible, maybe even more or less the same order of magnitude of the quadrupole modes emission. This is actually, again, one of the cases I've decided to consider. Well, it's really low compactness, but medium value of the orbital angular momentum. And you see that the relative phase in this case is 5 pi over 6. Well, I probably should have said that before, but we consider just relative phase of integral multiple of pi over 6, just for, well, because it was easier, let's say, it was faster in certain sense. And what we can see is that the contribution of the odd modes is for sure not subdominant, and the amplitude of the emission is almost of the same order of magnitude of the quadrupole mode emission. Even probably bigger, let's say, well, another observation that we can do is look into the luminosity to gravitational wave. So here we have the, it's probably hard to see, but the solid black line, which represents the total contribution of this luminosity. A dominant contribution is given by the quadrupole modes emission, this dashed blue line. But you see, in all the dynamics, also the odd modes, the 3 modes, is present, is not negligible for sure. Okay, so far we have been considered just the angular momentum and the relative phase contribution, but isolated. Now let's see what happens if we join these two parameters. So several configurations having the same orbital angular momentum but changing the relative phase can result in different outcomes. That's one example. So we are now going to even higher value of the orbital angular momentum. Again, one of the less compact configuration. And again, we have this video of the real part of the scalar potential. So on the right of these slides, there's also the integrated mass in all the numerical domain with respect of the time coordinate. So again, we have this dashed vertical line, the first one, the leftmost one, which represents the merger of the two stars. After the merger, there's a formation actually of m equal 1 hypermassive rocket star, which, well, let's also start with the video, which has an excess of orbital angular momentum. This allows the star to support an excess of mass. But what happened that this angular momentum is for sure dispersed through gravitational waves as well as the mass of the system. Well, the star then undergoes to a collapse because the orbital angular momentum now is not enough to support this excess of mass, and we have the formation finally of the black hole. As you can see there, the final drop of the integrated mass. Just to point out, there's also, you see, a kick, and we consider that in a certain direction, seems to be north east. We consider it is to be related to the dispersion of the mass on the opposite direction, so southeast. However, now let's go. Yes, go on.
What's the initial state? Are they? Do they have the same alignments?
I'm sorry.
So how's the initial state? I mean, it's not very to be a geek. There must be some difference, which I can. Do you have a difference in the phase?
Yes, it's still a configuration with 5 pi over 6 in this case. But what we observe is that this is the point of this part of the joint contribution. That in general, we said before that for this configuration we have also odd modes, no? But we are going to see in a bit that that's not true for even the antiphase configuration.
Okay.
Yes.
So you said you have the formation of a black hole, but on the plot, for instance, we don't see the horizon, right? So is it like small in the middle, or is it already encompassing?
It should be there, because I think I also calculated the integrated mass at that value, but I think it was continuing until the integrated mass went to 0. So I think that the hole is there, it was there.
But for instance, only on the XY profile, is it like say at the final frame of your video, is it big, or is it Like, is it like a small thing in the middle that we wouldn't see here?
I
Or
think
is it
I think it was small, but now we saw the snapshots. I think it was wait. Yeah, like there it was, but this was small there. At least it was be considered because I mean you see also the snapshot goes further than the extension of our integrated maps. So there's I think after that part there's calculate of scope.
I was just wondering if, I mean, because if you don't, say superimpose the mask or whatever, however you do it, it could be that the field that we see is inside the horizon of the map, but if it's just more in the middle.
I think it's the middle, but maybe I can check probably one day that we can check that. Okay. But I think I can go with the next slide. So I was saying that yes, the joint contribution. Okay. So far, okay, let's see that. This first snapshot that I showed you was about this configuration of 5, 5, or 6. Now we go to antiphase stars, but with a high value of the orbital angular momentum. In principle, all modes should be suppressed, but it's not what we see in this slide. So this is the slides that represent the trajectory of the two stars on the right. And then on the left, we have the quadrupora modes emission and the 3-3 modes emission. So now the antiphase configuration of the stars results in a repulsive force. So like overcoming the possible gravitational collapse, the stars undergoes through several encounters, bounces back 4 times. And then this leaves for sure an imprint on the gravitational waveform. Let me stop now. Until the 4th encounter, where they just merge, forming, and we're going to see in a bit, an M equal to Proca star. Which is actually probably also worth it to note is that the odd modes are completely suppressed up to the merger. So it means that the relative phase is conserved, at least up to the merger. And they are activated because of the stability of the M equal to Proca star. Again, probably this could be even more clear with this video. So again, another video of the scalar potential. So, okay, we have several encounters, so close encounters, particularly we counted 4. On the 4th one, we have this formation of this spin M equal to Proca star. This star is unstable, so the instability of the stars trigger the odd modes, and well, if you take a look to the luminosity, you see that the odd modes are triggered exactly when the star appears, so after the merger. The star then decays to an M equal 1, hypermassive Proca star, and finally onto a black hole in the final stage. Okay. So we wanted to at this point understand better these how the orbital angular momentum can affect antiphase configurations. So we now consider 2 cases, one with a boost of 4% of speed of light and the other one with 5 on left and right respectively. So while on the left case we have more or less the same dynamic as before, so several encounters, M equal 2 and then M equal 1 and then black hole. It may be also nice to note the case on the right, where now angular momentum is enough to let the star having an hyperbolic encounter and just escape the one from the other. Well, you can see at the end of this video. Okay. So, as I said before, we need to find a catalog of gravitational waves in order to eventually single out a specific signal detected, for example, from this exotic compact object. And to do so, we need accurate numerical relativity simulations. But this means that we need also accurate initial data. This is, I mean, a well-known problem in numerical relativity simulations. We need to consider, for in particular non-trivial matter configuration, some kind of initial data that satisfies the Einstein constraints. So we need to build constraint satisfying initial data that can avoid some kind of spurious or artificial effect artifacts in the dynamics. And in the second part of the talk, we are going to see a code that we wrote in a specific formalist. I'm going to explain a bit, that can provide constraint satisfaction data for several matter configuration, including binary stars. Let's start with the formalist. So we start with a fully constrained formalist, in which we know we can do a 3+1 conformal decomposition of the metric. So it's all quite clear. What I want to just stress is that the conformal metric has a deviation from the fiducial flat metric given by this tensor hij. When we assume this tensor being equal to 0, so meaning that conformal metric corresponds to the flat one, we have the conformal flatness condition. In this framework, in general, we have this elliptic system of elliptic equations that are in principle governed by the Hamiltonian momentum constraints, in which here appears these star quantities, which are just simple the conformally rescaled energy density, momentum density, and the trace of the stress energy tensor. However, elliptic equations suffer some issues of uniqueness and existence of the solution, depending in particular on the boundary condition that we set. We know that for maximum principle, if considering this general elliptic equation that you see on the bottom of the slide, if some particular sign is respected, we can at least have a guarantee of local uniqueness. When we rewrite this elliptic equation using the large function, the conformal factor, a wrong sign appears. So we have a non-unique, non-local uniqueness problem. And our idea was to use this framework, the extending conformal flatness condition, that was presented by Gabriele in 2009, which want to overcome this issue. And the idea is just to consider the extensive group of the tensor decomposed into other tensors. The first one is the longitudinal component, and then we have the transverse component. Choosing a specific value for the variable z and sigma, we can get conformality sandwich like decomposition, or as well the conformal transverse traceless decomposition, which is the one that we are implementing in this framework. Well, the two for sure can we can go from one to the other in with this easy way. So with this framework, these are the system of elliptic equations that at the end we have. Well, starting from momentum constraint, the composition of the group tensor, and so on. Within this framework, we build a code, and this code is called Incipit. Well, it's a really, well, long story short, let's say, in a certain sense, my supervisor asked me, okay, let's find a name, and they told me I don't know, something from your country. I'm from Italy, but in particular from Rome. So I said, okay, let's try to find a word that Roman Empire approved, and so I considered this word, which is the Latin for beginning. And also used in Italy because we used to indicate like the first sentence of a book, in which in general the author like just tried to catch the reader. More or less is what we want to do. We want to catch readers, let's say, showing that our results, our initial data are more accurate than, for example, using superposition. And the simulation that they have, so the dynamics, could be more accurate because they have better initial data. Now, the structure of the code is more or less the one you can see here on the scheme on the right. So we start with an initial guess for the metric components. We have a specific matter profile. Well, for sure I put a zero because what we need for my Boston star. So then we can compute the conformally scale component as stress energy tensor. And then we are going to solve this system of equation, the one I just showed to you before. I want to say that the code has a really hierarchical structure. And on this hierarchical structure, the uniqueness completely relies. So we have to solve this equation in that way. Finally, we get a solution of the metric components, and we can reupdate the metric, and so the code will like iterate this procedure until at the end global convergence is achieved. Here you see more or less some characteristic of the code that we developed. I want just to point out some points. Uniform read. It's not probably the best feature that we can have, but it's what we can do, uniform read. Then it's based on fourth-order definite difference discretization. We have complete 3D, so with no symmetry, but for sure the equatorial symmetry could be assumed. Actually, all the results I'm going to show now on are obtained considering just 3D with no symmetry. And the solver for the elliptic equation is this scalar relaxation Jacobi. It's an iterative solver, which requires to specify a specific relaxation threshold. And finally, we have an MPI parallelization scheme. For sure, we are working in 3D, so we need to do that. Another comment that I want to say, again, all the results I'm going to show now on are obtained using my-Nostrum file. So we use this supercomputer to have all these results. Okay, before going to the physics, let's say we consider just two toy model. The first one is a complex massive scalar field with a Gaussian profile. And here I'm just showing you like a convergence test. Is the Hamiltonian constraint violation along the x-axis. You will see all the plots have the axis rescale, well, normalized to 1. They are normalized with respect to the length of the domain itself. And we have the low resolution in solid black and the high resolution in dash red and green that are scaled respectively by fourth order and third order convergence. And we can claim that our convergence there is for sure between the 3 and 4, at least for this Gaussian scalar field profile. Then we move to a toroidal configuration. So here we assume a configuration that can also rotate, it's spinning. The angular momentum number here is equal to 1, so we choose the lowest value. What we realized was that we couldn't consider low resolution. We should go to higher resolution. The code was not able to actually find a solution, convergence solution. And here is again a convergence test, but consider the x component of momentum constraints along again the x-axis. Well, the lowest resolution is a scale, is in solid black. The highest in dash red, but it is scaled according to second order convergence. So we are losing a bit. It's not what we theoretically expected. What we can assume eventually is that this configuration has a non-trivial longitudinal, well, extrinsic curvature tensor, non-trivial symptotic symmetry, and we are working in conformity flatness. So, and also eventually it could be due to the fact that we are not in the asymptotic convergence regime, so higher resolution could be required. But just to point out that for the finest resolution here, the computational time required for convergence was already 2 days. And since we wanted more to focus on physical results, we just accepted this second order convergence. Now, let's go to the main part. So building constraints satisfying initial data for boson stars. We just consider mini boson star, so with solitonic potential and spherical symmetric solution that were provided by a code actually developed by Claudio here. And here you see well the mass frequency profile. These red dots are the configuration that we consider in this work. For simplicity, we just consider equal mass boson star, but binary boson star, but we can extend it for any kind of configurations. And we know that, yes, some codes now have been developed to build constraint satisfying initial data for several matter configurations. However, superposition approaches are widely used in our simulation. So what I'm going to show you next in these last slides is a comparison of our results with the superposition approaches. Okay, and it's probably the first result that we should consider. Here we have a comparison of the L2 norm of the Hamiltonian constraint violation with respect of the frequency for these equal mass binaries, obtained through our approach with this solid black line, and the red is again with higher resolution or scaled according 3.7 order of convergence, which is again in agreement with our theoretical expected value, comparing with the superposition approaches, simple and improved, respectively in green and red. So, to point out about this, let's say this, divergence we have for less compact configuration, what we can say is that the local convergence is achieved, so the Hamiltonian constraints on the x-axis has a fourth order convergence, but maybe the choice of the threshold was not low enough to guarantee also L2 norm convergence. And the second point maybe is worthy to stress is the fact that our results are always well below the results obtained through superpositions, even if the superposition L2 norm violation are obtained using a higher resolution, so 250 points. Just to say, NP represents the number of points per axis. Probably I didn't say this before, but it's quite important to understand these thoughts. Main drawback, computational time. So you see the lines goes up really fast, let's say. And we start with the less compact stars. We need like several hours, actually 1 hour more or less to 2 hours more or less to have a convergence. And for the more compact configuration with the highest value of the resolution, we need almost 2 days. So it's quite a bit.
Sorry.
Yes.
On what node?
No, that's
It's
no. On nodes.
Okay. But this is like the real lifetime.
Yes.
It's not like the
Yes. So yeah, it's a bit. But I mean, it's the other way. You have nice initial data, but you have to wait a bit.
Sorry, the bottom of the line is at equals 0.
Yes. The initial configuration.
Also, for the button on the left, for the convergence, could it be that in the less compact regime, then there will be more effect, like in the middle, say, than when they are more compact?
Yeah, I think it's like the field is more dispersed, so probably somehow can affect the. Also, we consider like the same separation for all these configurations, so somehow it could affect. I think we should also maybe try to go to lower threshold just for this configuration and see what we get. But we are happy with the results, so I think it would be fine. Okay. And this is maybe a picture that can make clear what I'm saying so far. So we have the Hamiltonian constraint violation on the equatorial plane for our approach on the left, and superposition, improved superposition on the right. So we see that the floor error in our case is of the order 10 to the power minus 12. On stars location, we reach the maximum, which is 10 to the power minus 6, 7, which is actually the floor value that we have in superposition. So there's a clear improvement in the results. But that's not so. Yes.
Sorry, yeah.
Back with
I
that.
mean, just because
Yeah.
it's hard to compare colors with
Yeah.
So
It's
on the right,
perfect.
at the location of the stars, what is the value more or less?
It should be -3. If I'm not
Okay,
wrong.
but there's also, it's not just in the bulk, there's also a pure improvement.
Yes. I think we have more or less. It was like 3 or 4 order in the stars location and more in the boundaries. Let's say. Yeah, I mean the scale is quite small, but it's also difficult to see with this color. But
But I mean, it's the usual thing, right? That if you put different background colors,
Yeah.
you are not able to tell. But yeah, okay, thank you.
Okay, so I would say that's not all, because we said, okay, let's try now to go with configuration, including also angular momentum, and we consider just linear angular momentum, sorry. So we are now boosting the stars towards each other, and we also needed to change a bit our solver. In this case, we have two stages. So the first stage we solve for the labs function and for the conformal factor. Once we get a solution, we go for the shift vector, activate this iteration, and then to guarantee consistency, the code has to alternate these two stages until, again, global convergence. And these are, again, some convergence tests that we performed for this specific case. We vary the boost from 1% of speed of light to 20%. And, well, again, we have a 3.5 order of convergence, comparing the black line, which is the low resolution, and the red line, which is the high resolution. Cool. And we also try to compare with the simple superposition, but probably in this plot is quite not clear. We're going to see in a bit in other plot something better probably. Just want to point out that the convergence order is completely recovered in the start position. That's a sort of dispersion again going to the boundaries. And yes, this actually is the complete picture of our results of this of our approach. No, one of the highest value of the linear angular momentum we have on the top lines the Hamiltonian constraints violation on the equatorial plane, both for our approach on the left and superposition on the right. On the bottom line, we have the x component of momentum constraint. So it's clear the gain of several order of magnitude for Hamiltonian constraints, the same that we saw before, more or less. For momentum, we have almost one order of magnitude of gain in the stars location, but at least we are like avoiding these spurious oscillation that the superposition approach introduces. So we can say that our results can form more accurate initial data with respect to simple superposition and for sure the improved superposition. Okay, so to conclude.
I was expecting you would show some observables as well. I mean, how the waveforms compare.
I have it, but still not there. In the sense that this is actually the result from this paper that we are going to submit in some hours, probably, on archive. About the evolution, we are working on that. I have some results right now, but I think probably we need some more. What I can tell you is that the evolution of the violation of the constraints is for sure better in the case of construct initial data with constraint-satisfied initial data than superposition. Then regarding the waveform, I think I need more results to say something else. Okay, so let's go to the conclusion. We know that gravitational wave astronomy is an important tool. It's a crucial tool that we nowadays have to probe echoes, exotic of dark compact object. We saw that also the wave-like nature of this object is encoded on the gravitational wave emission. So if we want to find this object through gravitational wave, we need consistent simulation, meaning consistent initial data. So our code is going in this direction. For sure, further developments will require a comparison of our formulas with other formulas, going behind the conformal factors condition, and build initial data for Proca stars binaries. And well, now that's all. Thank you.
Thanks, Gabriele, for the nice presentation. So we have time for questions. We have maybe Ekta.
So maybe I missed this, but what do you do so how do you control the constraints over the evolution? Do you use something like constraint damping, or is it just that the constraint?
You mean where in which case? In the case of the eccentric merger?
In general.
Okay. No, okay. In the second part, we didn't do any kind of dynamics, so we just considered building initial data, and that was it is. For the eccentric merger, no, actually, we just check how the constraints were going, and that's it. It's a free evolution.
So you use VSSN?
Yeah.
Why didn't you use, for example, CC4? Because the constraints.
Ah, so well, no, you're right. I think no, it's easy4. Sorry.
Okay.
Sorry. Yeah, you're right.
Because I was wondering if the formulation anyways dumps away the constraints. I would expect that maybe it can tolerate some violations in the beginning. So I was wondering how much difference it is.
Yeah. I think your question is more related to how can we say that initial data, like constraints satisfy initial data, can help to the evolution, no?
Right.
I think this is something that we should like consider properly, but we know that somehow some artifacts can enter, no, when you consider, like for example, the junk radiation that you see in gravitational wave at the beginning is due to the fact that you are building constraint variety initial data. And what I can tell you, for example, about that is doing some dynamics for actually this model. Yes, we don't find this high value of the chunk radiation at the beginning. So I cannot tell you a priori that yes, we are finding something completely new physics. No, I'm just saying that maybe we can rely more on results obtained through constraint satisfied initial data than with constraint violating.
So I was a bit confused. I didn't completely understand what was the role that played the fully constrained scheme that you mentioned before.
Yes. Well, I mean, it was more to introduce the formalists than something else, but the idea is just to consider that we start with this just say that we start with this decomposition, then we go assuming conformity flatness. That was more or less the point.
But this is fairly general.
Yes,
right?
it is.
The sort of fully constrained formalism is something that you use for the evolution, right?
Yes.
So for the purpose of just building the initial data is not something that you actually need, right?
Yeah. It just to introduce actually what we are working on, which is this formalism. Just saying that, and not saying that we use somehow that because I mean it's for dynamics, not from the initial data.
Right. Okay. So you basically you build the initial data with the XCFC.
Yes.
And then do the free evolution.
Going to the dynamics, yes. Again, still we don't have enough results to say something about dynamics, but for what we saw now, it seems to be fine. Let's say.
With the
Yeah.
free evolution. But,
Yes.
So you plan to also use the constraint scheme or?
I think it could be worth it. I don't know. I think it's something that we should explore in a bit. Really, that's something that we should go in that direction for sure.
Yeah, when Lisa is writing.
Okay. Well, she knows more than me. So it's fair enough.
Well, I don't know either if you want to speak directly actually or. So I can also read them.
Yeah.
So she says we can also explore different formulations for the dynamical simulations, also including Hij non-zero, but the difference will be small.
What, sorry?
But we can also explore different formulations for the dynamical simulations, also including Hij non-zero, but the difference will be small. Actually, I just want also to ask a bit of a follow-up of Hector's question. So from what you say, it's going to be okay, but I was wondering, maybe you have, constraint satisfying initial data, but just with the evolution scheme or the evolution grid, after a few times that whatever initial data you use, the constraint variation already jumps.
Yeah.
But you seem to say that actually it's okay. It stays.
I mean, as I said, I think further analysis are required in that sense. I can see your point, but principle, we know that if we solve the constraints initially, they should be solved in the evolution. But I mean, we know it's not exactly in this way, numeric. So
Yeah.
I don't know. I think it must be some real comparison. If you also look to other works that did more or less something similar, they were comparing also the violations. So, and you can say that's like a really huge difference considering constraint violating or constraint extension data. So we're expecting to have the same dynamics, but so far.
And well, and the other point is, I guess this may also depend on where you are in the parameter space, right? Like maybe in some cases, the superposition would be kind of okay, but in some other parts, the constraint,
we know that.
So the initial data would be.
Yeah, no, we know for sure that we put the stars so far apart from each other, so the position is fine. But this is actually the other way around, because also putting the star close enough, quite close, we know superposition cannot actually happen. So another mechanism to build initial data could be useful for sure.
That's a little bit why I was asking about observables. It would be, well, very revealing to show
Yes.
cases in which you have some observable to be severely different in the case in which solve constraints and the case in which you don't. So
Yeah, I think that would be quite important also to prove that what we are doing makes sense.
it's really important to make the difference very different.
Yeah, let me just read the follow-up in chat. So it was saying that not all the numerical errors are indeed controlled if the initial data is not good. Yeah, do we have other questions? We have still a little bit of time.
Well, how can you do like non-grid evolutions with our available computational data?
Well, we did in a long period, let's say.
How long?
I think it was several months now, I don't remember, because it was at the beginning of my PhD. And
It's very good. How are you able to get so much computational time in the class?
well, it's not by us. It's we have our own cluster also in Valencia. So
You can do whatever you want.
We used to have a priority, but now it's not working properly, and that's why I moved to my Nostrum, because my Nostrum, we have more time in my Nostrum, but in Valencia we have cluster and we can use that. So then we don't have to ask for hours like my Nostrum.
Let me ask if there are questions online, since there are a few people. In the meantime, I will update you on the chat. So she was saying also, especially if observables are associated to tiny quantities, since numerical errors can be more significant. So it was about the numerical artifacts. And also here, Cartesian coordinates and equispace grid were not optimized to reduce computational time. Yes?
Have you tried using different relaxation methods?
I have, but actually I found out that SRJ was, I can say I've tried like several. I tried just another one. But I have to say SRJ was the best for the problems we were trying to solve.
Well, actually, kind of related, I suppose, but you were talking about comparisons with other frameworks, so it was preaching my parish, right? But maybe you look at that, or I could try to make some comparisons. I know it's not necessarily easy to get into it the first time, but to have some comparison could be interesting.
I think that it's fair for codes to compare with other codes that does more or less the same thing.
I know that this formalism can be also used to compute binary neutron stars.
Yeah.
Actually, we have already about that. How difficult you think? The question is in this direction. How difficult you think is to add a scalar field cloud around this binary neutron star? You already think about that in the
I mean, I don't know so far, in the sense that I've never tried that, so I cannot tell you exactly.
But you did it in a separate,
Yeah,
in separate way. You already
We
did a
exactly.
cloud and also a binary.
That's the point. We already have like separately some binary to stars initial data and for our cloud. So I think that must be a way, like the best would be, I don't know, for example, more or less faster the convergence, assuming as initial data the like sort of superposition of your this metric, like initial guess for the metric, and then leave the code finally. So it should be growing this way just to get something faster.
So remember that in the case of the binary neutron star, you don't have problem with the compactness, right?
Well, we had some problems going to really compact configuration, but like not in the sense that the code could not converge. Like comparing with the results, we were comparing the case with for example, we saw that there were some deviations going to up to really high compactness. So I cannot tell you what we can get, but I mean, we are trying that, so let's see.
Yeah. We are very confident that we can obtain the
I think it would be worth it to try, and probably would be even fine, but let's see these days.
Okay, so, well, we've had plenty of questions and discussions, and Gabriele is still here for at least a week, so I think we can stop it here and thank Gabriele again.